Okay, welcome everyone. We're very happy to have Parthe again with us, this time physically. So Parthe is from UC San Diego, where he's doing a postdoc. Before that, he was at UCLA for his PhD, where he did some. He has been doing great work, and in fact, it's been recognized also by awards, notably the IIT Student Paper Award. Before that, he was in Mumbai, at IIT Mumbai, for his mathematics.
Thank you so much. So this is there's no theory in today's talk, so sorry about that. It's going to be a largely engineering effort toward large kernel models. So we're going to take a class of models called kernel model and scale them up to massive scale, about an order of magnitude bigger than what was previously doable using other algorithms. This is joint work with Amir Ehsan, who's a PhD student at UCSD. He's advised by Misha Belkin. And here's my outline for today. I just want to go over some background and motivation to consider the problem of large kernel models. I'll then share the results that we have, what we found out. And then I want to share some math details of this algorithm. I think it's an interesting algorithm. And so I'll go through the previous two versions of the algorithm, EigenPro, and then this is the new algorithm that was proposed in this paper at ICML this year. I'll do all that on the board. So let's get started. How many people here know kernel models, kernel methods? Have ever heard of kernel methods? Okay. How many people here have heard of linear regression? Okay. Oh, it's good. All right. So here is like a broad question. We're all interested in machine learning. Neural network performance. Anybody who has an answer to this question can potentially make a $1 billion. Let's see. But here are some answers that the community has come up with over the last few years. There is one really nice paper by Kaplan and co-authors, which is about the scaling laws of these large language models. And what they actually observe through their analysis, which is largely empirically driven, is that performance of neural networks at these large-scale applications depends more strongly on the scale of the problem. Performance depends very weakly on other architectural hyperparameters such as width and depth. They have several ways of calibrating this kind of a thing. There's another follow-up paper by Hoffman and co-authors, which essentially did a further analysis of an empirical type. And their observation really was that we need independent scaling laws for both degrees of freedom here in solving a machine learning problem. One, which is the model size, and what they call train size, which is really just the size of the training data that you can use.
So what is scale here? Scale is the amount of data you have?
Scale is the amount of data you have, number of samples. But also scale is the size of the model. So both things are being
So that's under your control.
Yeah, you have this control on how many parameters you want to your model. You also have control on how much data you want to use for training your model, given a certain budget of computer.
Training time is not an issue.
But training time is also something that Hoffman talks about in detail. So what they observe is the more you train, the better your model gets, which is well, one can say post hoc that it's a natural thing to say, but they actually calibrate it as to what.
So, but is a scaling law there or something that?
There is a scaling law there as to how it depends on the training type. And so the sort of main observation through all of this is that most strongly neural networks seem to perform well because of their ability to scale flexibly, which is that you have good control on being able to change both these aspects of model size and train set size. So here's one plot from Kaplan et al.'s paper, which so what is being plotted here is on the y-axis is the test performance, so lower is better. On the x-axis is number of tokens processed, which is loosely equivalent to the size of the training data that. And what each color is saying is the size of the model that is used to use with this particular configuration. Yeah. So what the main message here is that larger models require fewer samples to achieve the same performance.
Is that obvious?
It's not kind of obvious.
Overfitting could essentially just kill it.
Right. So that's kind of one of the hard truths we are all dealing with in machine learning today, which is our classical analysis tells us that overfitting is a concern. But what we see in practice is that overfitting is not really a concern. We see this benignness that comes out of all the models that we overfit, but they still generalize that. So there is some kind of
Is this across all aspects of machine learning or particularly just vision and text? This overfitting is not an issue.
So this is all high dimensional aspects of in all high dimensional problems is what we actually see. Where the dimension of the input is very large, this is kind of the behavior that we see consistently. So yeah, vision and NLP are just some examples of such problems. And at the same time, there is sort of a surge of interest in this classical set of models called kernel models. Personally, for me, this paper from 2018 Europe's was really eye-opening. This paper really set out this framework called neural tangent kernels, which essentially says that the kind of functions that you learn by training a neural network are something that are well represented or well analyzed in this framework of kernel models or kernel methods. Something that is very well understood mathematically, something that we can hope to do a lot of good theory. Right? So, in some sense, this kind of set the aspirations of what can be achieved in terms of mathematically understanding what goes on in neural networks, which until 2018 seemed like a really hopeless question to begin with. Right? So, following this paper, there has been a real surge of interest in kernel methods in all aspects. We've seen a lot of behaviors that were empirically first demonstrated in neural networks being actually replicated in kernel methods. So regarding kernel methods, there are some key questions which still sort of stand apart. So one of the most important ones is how can we close the gap of performance between kernel methods and neural networks? And I've kind of been focusing on these questions for the last couple of years. And to sort of answer this question in a more quantitative manner, we pose a more specific question, which is what are the scaling laws for kernel models? Can we characterize those scaling laws in some sense? But at this point, we sort of did a roadblock, which is how to scale these kernel models. There are some computational hurdles that exist that prevent us from scaling kernel models to large data problems. And that's what I'm going to be talking about in this talk. Yeah. So what are kernel methods? This is broadly the setup of what we consider in supervised machine learning. We want to fit a function of the form y is equal to f of x. And what we have is we have n samples of data of input-output pairs, xi, yi. I'm going to assume that the inputs are in d-dimensional Euclidean space and the outputs are real time. And kernel models are nothing but simple type of I shouldn't say simple, but there is special type of functions which have this functional form, which is a linear combination of certain basis functions. Yeah. What are these basis functions? They're formed by these functions k, x, xi. So the k is a bivariate function. Yeah, and k is what is called a kernel function, and that's what gives it the name kernel methods. And this is going to measure some kind of a similarity between its two arguments. Yeah, so you can think of this term kxxi in this expression as the local influence of a training sample xi. Yeah, so here is an example kernel, which is the Laplacian kernel. As you move further away from a training sample xi, the influence decays exponentially. Yeah, that's the expression for the Laplacian kernel. And alpha I, the coefficients of this linear combination, are the parameters of this model, and these are the learnable parameters. So you would choose alpha I based on the data that you have and the targets that you have in your training system.
So in these situations, you fix a specific function.
Yes.
And then you're just going to learn what possible alphas will best explain.
Yes. Perfect.
But then you actually have to store all of your samples.
That's right. Yes.
Oh, okay.
That is what causes the problem of scaling. It's a good point. So yeah, you can think of the coefficient alpha as some kind of local or a global influence of these training samples. Right? And typically these alphas can be learned by solving a certain linear system of equations of the form k alpha is equal to y, where k is the n by n matrix whose ij entry is the kernel evaluated at xi and xj, the two training inputs. And the right hand side of this equation is the vector of all the targets that we want to fit. So I guess I can skip over this part. Well, you all have seen linear models, so I guess this is one way of writing the predictor that you get by solving a linear model. If you your prediction function at a new test sample x is going to have this form, where alpha are solutions to this linear system of equations. So x transpose plus lambda inverse. Kernel methods are sort of nothing but a version of linear models, where instead of using a linear predictor, you use a feature map and then you use a linear predictor on top of that feature map. And when you do this, this feature map can be from the input space to any kind of input space. And when you finally write down your predictor, it's again going to have the same expression, a linear combination of inner products of these features, where the coefficients alpha again will solve a linear system of equations of this type. And what kernel methods essentially do is they allow you to not have to specify these feature maps at all, not have to deal with these feature maps at all. What they give you is some kind of oracle that tells you what this inner product is without actually ever evaluating what that feature map was. Right? It's a shortcut to get that inner product between those two.
But your scaling problem with number of points, there's some kind of clustering that you're going to do in some way, or?
I'll get to that soon. Yes, I have to do something like that to make the scaling problem a little better.
Maybe it's a different question. So when you say a neural network, you're going to compare a kernel method. In neural network, you don't have to specify what kernel you're using. It will produce on its own whatever function is being learned.
Right.
Here you have to specify a k and then learn alpha i's.
Correct.
So whatever choice you will make, it will be very delicately dependent on the kernel you will choose for yourself.
Absolutely. Yes.
So what's the intelligent way to actually do this?
So I am not talking about that today. So for today, we just assume that we are going to specify k. But choosing k is the important, the secret sauce in how well a model is going to perform.
Are there typically 2 or 3 choices of k, or is like very variable?
Yeah, there are many choices of k. In fact, if you choose a neural network architecture, there is exactly two choices of K that really nicely capture what the behavior of the neural network is going to be in a certain function.
So the choice of K seems similar to the choice of the transfer function in the nodes of the neural network. Right? Are they related?
I'm not sure I follow.
You mean the activation?
That's the activation.
But it is a little different.
There is some relation, but they're not quite directly related. Yeah.
And you will not parameterize K in some way, you can learn the parameters.
Today I'm going to assume that someone has chosen the K for me, and my task is only to find these alphas. So yeah.
In your previous talk.
In my previous talk, I was talking about how K can be chosen in a smart way that does feature learning and whatnot that neural networks do, and how we can improve K by choosing a K smartly. Today, I'm just going to assume K is chosen for me beforehand. Yeah, and I'm only going to learn these alphas. Yeah. So yeah.
So is there any assumption on K, like for example, do we want to say that once you fix one of the arguments, it's maximized only when the second argument is equal to the first? Or is there no assumption that we need for?
You need positive definiteness as the assumption of K, positive semi-definiteness as the assumption. So any kind of a matrix that you construct by taking pairwise kernel evaluations, any such matrix will be positive semi-definite. That's it. That's the only assumption. Okay, so here's what is the issue with these classical kernel models that we've been seeing so far, right? Like there are n learnable parameters. N is the size of the model. That's what this would mean. But n is also the size of the data set, right? So the size of the model and data set are very tightly coupled. At the same time, there are some scaling related issues related to how you scale in terms of the size of the data set. I'll get to that in a sec. What I'm going to talk about is a different class of models, which I'm calling general kernel. So what is different here is that instead of xi being used as the second argument in these basis functions, I'm going to use some zi's, which are some points that are chosen in the domain. Yeah. And this kind of a model is also something that has been studied in the past. Every decade, there is something that people have studied. Different aspects of approximation theory, what they were considering in 90s. In 2000, they were considering some clustering unsupervised learning problems. In 2009, they were considering some supervised machine learning problems. And this model had grown up before. So this model family is kind of not new. But what's really nice here is that you've chosen these centers, and that gives you this degree of freedom of the number of. You can now have a model size which is different from the size of the data sets. You created a decoupling in some sense, and that gives you this flexibility that we were looking for from the scale. And typically, you would choose P, which is much less than 10. That's fine. And so now, if you were to just compare some complexity kind of expressions. Typically, to train for one epoch on a given data set, this is the kind of complexity you're looking at in terms of n and p. P is the number, the model size. So this is again much cheaper than O of n squared. What we do need for training these models, or at least what the state of the art was until our paper came out, was O of p square was the amount of memory you actually needed to train these models.
Where does the p square come from?
That will come when you write an algorithm to train this kind of model.
So the xi's are the data, the training data.
Xi's are the training data.
The zi's are something the model finds out, or is it given to?
Right. So again, today I'm going to assume that they've been given to this.
So also is there a benchmark, because I will always have a order one algorithm for something. So you're comparing these two, how are you comparing the performance?
Test error. You want to get good test error.
Least squares.
Yeah, I'll be talking about test accuracy typically is what we look at in these classification kind of problems. If they are regression problems, then least squares. So yeah, the key takeaway is that these kind of models, general kernel models, can be trained on a data set of any size, which is not the case with these classical kernel models. N is kind of restricted because your budget depends a lot on N, size of the data. The limitation is that what we observe in practice with in neural networks and in kernels is that training on large N requires you to use large P as well if you want to get a good performance. Because at some point performance saturates when you keep P fixed and you don't grow P with N. And so our contribution in this paper was to reduce the memory for training these kind of models from P square to P. Again, in this I'm going to assume now that these ZIs are fixed, somebody has chosen them for me. I'm again doing some cheating here somehow, but this still remains a hard problem in spite of this. Okay, so here are the algorithmic primitives and constraints that I have to deal with. Yeah.
You say it's computational. What does it mean that it's a learnable parameter?
I can choose alpha i's depending on what the targets are that I'm looking at.
P is also a learnable.
Oh, P is the number of learnable parameters. That's
It's a
what.
number of learners.
Yeah, P is the number of learnable parameters.
So for you, in some sense, in this talk, I mean, like you might as well assume that the xi's are, except that there are just pxi's. Is that a reasonable thing to assume?
No, because Xi's are my training data, right? Like
But the zi's you're assuming are given to you.
Zi's are given to me. I could just subsample my data
Right.
to get P of those samples.
Okay.
That's one
Sure.
something that we will use in our experiments. Among other things, I'll show you some experiments. Okay, so here are the algorithmic primitives that we have access to essentially. So we can do this operation, which is the kernel matrix vector multiplication. Okay, so what is this? Essentially, if you are given a kernel, and if you are given two sets of samples, so these are my samples, these are my centers. So I'm going to call these as the centers of the model. It makes sense. And if let's say V is some vector of size P, then I can do this operation. So KXZ is a matrix of size N by P. Yeah, and then you take a multiplication with this vector.
What is D?
D is the dimension of the input.
Right.
Yeah. So there is a severe memory constraint here. The memory that I have access to really is independent of N. And I'm not allowed to store any kind of a kernel matrix at any point. No kernel matrix can be stored. And this can be satisfied by this primitive.
So the V is playing the role of holding the alphas that you're looking for.
Okay, yeah, okay. Yeah.
What is the K over here?
Sorry, this should have been 1. That's the 1. Yeah. Okay, so this is really we're thinking of a setting where the data is somehow streaming, where the number of samples is much larger than the number of centers, and you're getting data in some kind of a stream. And we are also assuming that the kernel evaluations are cheap. Each individual kernel evaluation is cheap. Yeah. So here is some comparison with previous algorithms that can train such models. So EigenPro 2 was an algorithm that Misha, one of the co-authors and one of his PhD students, had written earlier. That could only operate when the centers were the same as the data, which means that they were only able to train classical kernel models. This Falcon algorithm was able to train these general kernel models, but they had this p-square complexity in the in terms of the centers P. Right? And so they could only train models up to 256,000 centers. That's where they would run out of memory on modern hardware that is available in clusters easily. But what we can do is we can basically scale very easily beyond their constraint. So if we were to actually look at the performance in terms of test accuracy for a given data set called debris speech, where you have some 5 million samples. This is what the performance looks like for these three algorithms. The blue algorithm is our algorithm. As you keep increasing the model size, you can see that the performance keeps getting better and better for the same data. At this point, however, Falcon runs out of memory. You can't train this big model on today's computers easily because it requires a RAM of a terabyte to train this model.
So in this case, model size is P.
P.
Okay.
The number of centers, yeah. But we can very easily scale to 1 million, and we'll soon have another paper which talks of like a 10 million model size. It scales very nicely with the number of centers in the model. So,
right, so I have a question. So, why is it that Falcon is doing worse than EigenPro 3 for the smaller sizes?
that's a great question. Actually, so the solutions that are found by both these algorithms are through iterative procedures, and they are different solutions.
Okay.
And turns out that they have different properties. We don't quite fully understand why there is this gap between these. Okay.
I didn't follow the question.
So his question is, if they're both solving the same model, if these two algorithms are both solving the same model, why is one getting a better performance than the other? Okay. And the reason is that the algorithm to train is a different algorithm. So the algorithm itself bakes in some bias, which seems to be helping us in this. Yeah, so I guess there is this one nice thing that we can now do with this kind of a general kernel model. We can do this data augmentation, which is one of the most important strategies that we apply in machine learning today. So what is data augmentation? You take data, but you keep modifying that data and you keep using that same modified data multiple times. So you just multiply your original data set by adding perturbed versions of that data set. And you get a lot out of this when you do this in practice. And typically, if you were to train a kernel model, you would have been stuck at 88% accuracy. But when you now do data augmentation, you suddenly get a 2% boost in performance.
So input data and you just kind of perturb it and you get more input data.
Yeah, that's what. Yeah,
And that helps.
that helps. Yeah, but if you were to do this augmentation and then train a kernel model on the augmented data set, that would have been really expensive earlier.
Yeah.
Now it's very much feasible. This is sort of what the problem is now.
So how the perturbation done typically to be effective?
So in images so it's very domain specific. In images, what they do is they crop out some part of the image and then they just feed those cropped out parts. They do flips, they do some rotations of images. In language, they just delete some of the words and put blank spaces there. Yeah, there are different ways of doing augmentation. There is no standard way of.
It's not like you had Gaussian noise that we were.
Well, that's one thing we actually do because we don't know better things to do. But yeah, that's also something that can help. But there are now also other things like robust learning, online learning, federated learning, which is now very much in the realm of what can be done with kernel methods with this new algorithm. So here are some results using this algorithm. This essentially corroborates all the hypotheses that we had about kernels based on what we see in deep neural networks. Right? So one such hypothesis is that adding more data improves performance, and we consistently see that this happens. If you take the same model size of a general kernel model, you keep adding more and more data, you can get better and better performance. Yeah, and this holds across all data sets that we. Right.
Can you add data incrementally, or do you have to, like, if you get some additional data, do you have to start from scratch and train?
So in practice, you have a data set.
Yeah.
What we're trying to study here are scaling laws. So we want to understand what would happen if you had more data.
No, but I'm saying, but for training, I mean, for getting these alpha and so on, do you have to start from scratch if you get more data, or
Yes.
you do have to start from scratch?
You don't have to start from scratch. You can just incrementally update.
can.
Yeah.
Now, these things are independent of form of kernel, this conclusion that you're making?
Yeah, this holds across kernels actually. We've tried this on multiple kernels. What I'm showing you today is all specific for the Laplacian kernel.
Right.
Yeah, but this observation holds true across kernels that you see.
Okay, and so right now you're just saying that with kernel methods, you can also scale, you can compete with other networks. So you trying to become comparable to the other networks. In what sense are you better than them?
We don't quite have a clear enough answer to make that claim yet. We're slowly hoping to get there. We don't have a clear enough.
What is other network? Are you believing that typical deep neural networks, they perform very well? You think kernel methods also perform really well?
But you haven't shown that comparison.
Yeah, that's what I'm saying. That's not a claim I'm making today.
So I mean, kind of moving in that direction, for sure.
Yeah.
But are there some advantages to kernel methods which are not true for neural network?
Right. So the advantage is that the learning problem of kernel methods is very simple.
Does it mean faster?
Uh,
I mean, definitely for it,
it's a little.
you can interpret it more easily, right?
More interpretable.
It's more interpretable. The training problem is convex, so you know that it's always going to converge.
But what does that translate to, I guess, in practice?
Right.
So does it always converge to the
More stable as a technology in some sense. Yeah, we still don't have enough evidence to make a apples to apples comparison between neural networks and kernels based on model size and based on model size really. Given a kernel model of a size in terms of number of centers and given a neural network in size given in terms of number of parameters, how do you compare these? Are the parameters equal to number of centers? It's not very clear. So that's the conundrum.
Sorry, so how should I know very little about this, but how should we interpret this? Should I say that as you make as you increase your number of training samples by twice or 4 times, you get some additive improvement?
Yes. Yeah. Yeah, that's the correct interpretation. Yeah, so we can again now use data augmentation. I showed you one example. This is just another example where if you keep adding more and more data, you keep getting better and better performance than you would have had without any augmentation. So here, Sandeep, we were using additive white Gaussian noise as the corruptions for adding new data. Okay, so here's another scaling curve, scaling law, which is for a fixed data budget. So if you have the number of samples are fixed, do bigger models perform better? It turns out that again holds true bigger in kernel models. So this was something which was observed in neural networks. This is now evidence that this holds in kernel models. So on the what I'm showing you are performance curves for different model types. And the curves that go higher and higher are higher in terms of the number of parameters or number of centers in the model.
So these centers are obtained by sampling?
Yeah, these centers are obtained by randomly subsampling the training data. That brings me to if you are smarter about how you choose your centers, instead of doing random subsampling, if you do k-means on your training data, training inputs, and then choose your centers, you actually get a boost almost always. So there are some data sets, you fix the model size, and instead of doing random subsampling, you choose k-means with k being equal to the number of centers you want to extract, and that gives you a performance boost, which kind of makes sense.
So yes, the same point again. So people do this mean field analysis of large networks. And then they say, okay, when we train the network, that's how the mean field moves. Will that be easier in this kernel regime or this kind of asymptotic analysis? They're more structured mathematically.
I would hope there is.
But not very done.
I don't think it's been done like that. I'd like to see something.
Yeah.
Okay, so now I'm going to talk more about the algorithm, which is EigenPro 3. This is an iterative primal optimization algorithm. So just some very high level highlights of this algorithm first. So you are trying to solve this kind of a problem, which is minimize the square loss subject to the constraint that you have the function lies in the span of these basis functions. So these are fixed. And so what is this? This is an infinite dimensional optimization problem because you are searching over this Hilbert space. But it has a finite representation in the sense that this subspace is finite dimensional. There are only p degrees of freedom here. So you can actually hope to solve this numerically. And yeah, this is a linearly constrained convex quadratic program. And the strategy that we will apply for this is projected gradient method. Yes, I'm going to start using the board. Before going that, I guess there's this slide which I can still use. So if we consider the projection subproblem in the reproducing kernel Hilbert space, in this particular norm, which is the norm that is governed by the RKHS, the norm that's induced by the inner product on the RKHS, then we have this really nice result about what happens to the projection. So if you were to project onto this subspace of the RKHS, and let's say G is some function that you're trying to project, then the solution to this projection has this particular form, right? And what are these coefficients of projection? Beta j. They are the ones that you get by solving this system of equations. What is this system of equations? K, Z, Z. So this is the centers and centers. The kernel matrix evaluated at between two centers. And the right hand side is the function being evaluated at the centers. Right? So you start with any function in the RKHS. You want to project it onto this subspace. You just have to solve this linear system of equations. And that's it. That's what gives you the projected function. And this is what we will use to do the projected gradient algorithm. Okay, so I'm going to stop sharing, I guess. We want to just discuss I mean, yes.
Sorry, just
Too late. Too late now. And then
How does this go up and down?
There are two buttons.
This one.
Or maybe there is several types of buttons, so hopefully some of them use it.
Okay, so yeah, let me start with. And F belongs to C, where C is equal to the span of I from 1 through B. I'm going to define some operators So Sn is this operator which I call the measurement operator. What does it do? It essentially just when you apply it to any function in the RKHS, it just gives you the evaluation of that function. Right? And what is the adjoint operator? The adjoint operator actually goes from Rn to the RKHS. So if I were to start at alpha, what is the output going to be in? It's going to be in the space of functions. It's going to be in the RKHS. And it's exactly this function. Okay. Now, what is this objective function? This is nothing but Sn applied to F. Y is essentially the vector of all y's. So now when I write the gradient of the loss function, let's call this L or F. This is the Sn star Sn F minus Y. And the projected gradient will be the projection phi the projection onto the set C of Ft minus the learning rate times now there are some things we can actually do here. So if Ft okay, first things first, this is actually a linear operator. The projection operator ends up being linear. And this is a how do I go up? Okay. So the trick is to start at a point which is actually in the model space. So F0 is also defined as P as another measurement operator. P of F is the vector of F evaluated at all the centers. The trick is to start at the point of this form in the RKHS.
Trying to achieve this preempting what you're doing.
Yeah, thanks.
Did you show the improvement in the algorithm? Is that?
Yeah, I was trying to derive the earlier versions of the algorithm, but I don't think I will be able to finish any of that in the next 10 minutes. I'm trying to recalibrate what is best achieved in 10 minutes.
Like where the improvement came from? Like, is there a particular property that you?
Yeah, so the particular property was really the projection step and how we actually got there. Okay, maybe I'll solve a slightly different problem that just give the flavor of what these RKHF gradient descent steps would actually look like in a that can be implemented numerically. So suppose I were to just run this update without a projection. Suppose I were to focus only on this update. And this is an update in the RKHS. This is not something I can actually implement on a computer because this involves function objects. But what is really nice is that if FT is of the form Sn star alpha t for some alpha t. If Ft lies in the range of this operator, then Ft plus 1 also lies is also in the range of the operator. Why is that? Because this object is of the form Sn star applied to some vector. Right? So you can write this again as the alpha t plus 1. Right? So what does this now look like? This is nothing but Sn star alpha t plus 1 is equal to Sn star alpha t minus some learning rate times Sn star minus 5. Now Sn f minus y is the evaluation of the function ft, and if ft is equal to Sn star alpha t, then Sn of ft I claim is the kernel matrix AXX times alpha t. So this is a claim that I want to. What does this do? This tells me that if I were to run this update equation, this only requires me to have access to the kernel matrix vector product primitive. So I can now implement this on a computer. This is equivalent to gradient descent in the RKHS. We know how to choose the learning rate such that this algorithm converges. So this is kind of the real starting point of all the algorithms that we build for learning these kernel methods in an iterative manner. If you were to use SGD instead of gradient descent, again SGD the RKHS directly, what you would get is an update equation which is of this form. Get K, X, M, where X and Y is a mini batch. You can again show that you start by writing an algorithm first in the RKHS and then you trace back how each term looks, and turns out that this is the update that actually is implementing SGD in the RKHS. What's also really nice is if you are in the RKHS, in an RKHS where there exists an interpolator. So suppose there exists an M star such that you can interpolate the data. Then there exists a learning rule eta, which is constant. Such that let me call this 1. This. Converges in the sense that FT goes to F star.
When the eta is constant, it depends on the norm of F star or something.
It depends on the norm of. Yeah, it does. Yeah.
Sorry, sir. In this case, if F star is in H, this so if you view the the problem of solving for alpha as a linear system, you're saying that there is an alpha, there is a solution to K times alpha equals.
Yeah. Right. Yeah, there is a solution to that system. So it turns out that SGD doesn't quite converge fast enough because the learning rate that you have to choose is something like 1 over lambda 1 of the kernel matrix. The largest eigenvalue of the kernel matrix. And here's the property of kernel matrices that is, well, it can be viewed as both problematic and useful, is that their spectrum typically looks like this. So you are really paying a very heavy price for having the largest eigenvalue be very large. So what do? You precondition and you want to pay a price which is much lower. So if you use a preconditioning strategy, is there a color? Oh, great. Okay, so you can use a preconditioner that essentially brings the learning rate to a much larger value. If you just multiply a preconditioner matrix here, the preconditioner that we actually end up using has a really nice form in terms of the eigenvectors of the kernel matrix itself. And then subsequently, we also have a much faster way of approximating what that preconditioner is, using something called a nice form approximation of the kernel matrix. So you never actually have to calculate the full kernel matrix to get the eigenvectors of the kernel matrix. So P is some kind of a low rank matrix. So P is a rank Q. that P times KXX as this as the spectrum. It has a modified spectrum which just gets considered. The same convergence rule applies with this as the new learning rate that is. So this was lambda 1 and this is lambda 2. What does this set of equations actually converge to? This set of equations converges to the solution to this system of equations. So it converges to this solution. So what's the difference between Pro 2 and Pro 3? Right. So this was Pro 2 actually. So this equation here is EigenPro. EigenPro 2 was so this box is EigenPro. EigenPro uses P using a nice strong approximation. So that actually reduces the memory requirement quite drastically. Going from 2 to 3, we essentially just write down the projected gradient descent iteration in the function space, trace back how it's going to look in the parameter space, in alpha space. And anytime there is a projection step involved, the projection step requires you to solve the projection problem, subproblem, requires you to solve something that's basically what do you call this? The h is some other function that you found out that you need to evaluate. This you can solve fast using EigenPro 2. So we trace the update equations of projected gradient descent, and every time we want to do a projection step, we solve the projection using EigenPro 2 itself. And that's what gives us EigenPro 3. So we don't fully solve the projections, we do approximately solve the projections, inexact projections. And that gives us EigenPro 3. So I didn't write down the equations of the EigenPro 3 algorithm, but they're not ready to write on the board right now. But like that's how the derivation would work.
Okay, so I have like a really naive question. So in your equation of GD and then following LGD, you write down the update step for the parameters, right?
Right.
So could I not have obtained it directly by using GD in the parameter space?
Great question. Answer is no. So if you had written it in GD, in the parameter space directly, you were looking to solve right?
Yeah.
When you try to write GD to solve this problem, you get a KXX square.
Oh, yeah, of course, yeah, I forgot it. Great. Okay. Could not have done that.
Right? So the price you pay for this iteration to converge is the condition number of k square.
Yes, sir, yeah. Yeah.
Whereas the price you pay for the convergence of that is just k.
Great. Okay. Yeah.
So this iteration, the gradient descent iteration is actually called the Richardson iteration. Paper from 1911. And that is really an algorithm to solve this system of equations. There are many algorithms that you can use to solve this system of equations that only require access to the kernel matrix vector product. Like conjugate gradient descent, for example, is also going to solve that. But conjugate gradient ends up being quite unstable for these kernel kind of problems. SGD, on the other hand, there's another name for the SGD, which is the Kaplan. I forget the date for the Kaplan paper, but that's also, I think, 1932 or something. So SGD is actually a randomized Kaplan method that we are implementing. So the analysis for that can follow from those.
So kind of reminds me of acceleration going from square to square root.
Kind of. There's actually, this doesn't have any acceleration in the momentum sense.
Yeah.
When you do that, you get even faster than
Okay.
this. We have another paper coming out soon and that's acceleration. Yeah. Okay.
These were fixed in all analysis,
Z's are fixed in all of this. Yeah.
right? And that's a separate line of work. How you-
That's separate line of work, how to choose Z's. Yeah.
And can you adaptively kind of based on data adjust these?
There are some ideas we are playing with right now to find Z. Yeah. No clear right answer here.
So you want a proxy for all the points in the space.
Right. So k-means is one strategy you can do. There is an adaptive strategy called randomly pivoted Cholesky that is some adaptive way of choosing these centers. Yeah, so still playing with some ideas to find the right centers.
So for k-means to work well when k is small compared to the number of data points, you will be having some condition like the approximate rank of the n samples is small or something, right?
So again, none of this has any theories so far, right? Like this is just a exercise in trying to get as big a model that you can train. Yeah. Ideally, you would want something like that for k-means to work.
But for typical applications where X is an image or something, is it typically residing in a much lower space? That should have a clear answer, right?
Typically, it doesn't lie in a single space, it lies on some manifold.
Yeah.
That's the understanding we have. But yeah, we don't quite know how to characterize that manifold, and so we don't know how to sample from that.
But it is a much lower dimension, right?
Yeah, that's the intuition it is. You would like to ideally sample from that manifold, that would be the right thing to do.
Sorry, like one more question. So, in your capital C, this rank Q matrix, so somewhere it should show up in the price you pay, right? It's not that it's completely free.
Right, it's not free. So it involves a matrix, an additional matrix vector multiplication.
Yeah.
That you pay a price for. But in terms of storage, are you asking?
No, I think in terms of the The number of iterations needed or convergence or something.
The convergence is much faster when you have this additional P.
Oh, okay.
Because faster in. Yeah, it's faster too. Because it's reducing your condition number by changing the condition number of this spectrum is really bad, whereas the condition number of this spectrum is much better.
No, that's fine. But I'm saying that are you still converging to the same point?
Yeah.
Okay. Very cool. I have the remediation question. Yeah, maybe.
So it's like solving P here and P here.
Oh, okay, fine. So that solves.
Actually, I misspoke. It's not a rank Q matrix, it's identity minus rank Q. So it's actually
Okay,
a full
yeah.
rank matrix. So you can
That makes sense.
cancel it
Yeah,
from
yeah,
both sides.
that
Yeah,
makes
thanks.
sense.
All right, that's fine.